One of the hottest topics in the scientific community is nowadays the implementation of quantum computer, which building block is known as a qubit or a quantum bit. Compared to a classical computer, a quantum computer will allow us to speed up the processing of massive amount of data, which could help, for example, scientists to untangle chemical reaction, leading to the creation of new medicines. Hi, my name is Fabio Ansaloni, and I'm a PhD student at the University of Copenhagen in the Center for Quantum Devices. My work is aimed to the implementation of spin qubits in silicon devices. But let's take a step back in order to understand what a spin qubit is. If you think of your classical computer, its building block is known as a bit, and a bit can only be in two different states, either 0 or 1, which can actually be seen as either the absence or presence of current in a common silicon transistor. Now, a quantum bit will be able to be in any superposition of these two states, meaning that the qubit is actually able to do multiple computations at once. Of course, quantum superposition of state is a fundamental property of quantum mechanics, and therefore, in order to define a qubit, we must be able to identify initially a two-level system which obeys the laws of quantum mechanics. To give you a rough idea of what superposition of state means, you can think of a pendulum which is oscillating in an xy plane, and its trajectory will be given by any possible linear combination of the motion along the two axes x and y. Now, if we create a new object which obeys the laws of quantum mechanics, which we call a quantum pendulum, its trajectory will be given by all of the possible trajectories which were allowed for the classical pendulum. Now, we cannot use a quantum pendulum to create a quantum computer, but at the beginning of this century, smart scientists came up with the idea of encoding a qubit in the spin of electrons. Spin is another fundamental property of quantum system, and it has no classical counterparts. You can think of it as if electrons were a spinning ball which behaves at the same time as a tiny magnet. Now, this tiny magnet can align itself with an external magnetic field. Therefore, we can identify the qubit as the system in which the two states are given by the configurations in which the magnet is either parallel or antiparallel to the magnetic field. In particular devices called quantum dots, it is actually possible to trap a single electron. Now, under specific conditions, for example, really low temperature, and in presence of magnetic field, it will be then possible to create a qubit system. In order to determine and to manipulate the spin of this electron, therefore the qubit, we will use fast electrical pulses. Here at the University of Copenhagen, we are developing a reliable recipe to create these quantum dots using lithographic steps, which will allow us to deposit electrical leads on top of a artificially grown crystal. Now, once this is done, we connect the devices to the outer world through electrical connections, and we loaded it into a dilution refrigerator, which can actually be seen as a huge thermos, which instead of keeping your coffee warm in the morning, it is able to reach temperatures which are close to the absolute zero. In this configuration, we will therefore be able to perform fast electrical pulses to control the state of our qubit.